Okay, it is my pleasure to introduce Liz Cushman, who's been with the survey for 2 years. Great. She came over from the dark side. No, not really. She came from GDP, which is a surprisingly common path on this side of the building. We have a lot of DPP folks who saw the light in the survey. And so her talk is going to be, this is a project we worked on jointly, and we're kind of excited about the results, and we have some fun toys. And with that, I'll turn it over to Liz. Get set up for you. There you go.
Thank you. Can we test my volume? I'm gonna try so hard to project. I'm so sorry that my voice is quiet, and to everybody online. What a good way to start a presentation by apologizing. Can everybody online hear me okay? Is this a good level?
Yeah, we got thumbs up.
All righty, great. Well, thanks so much for having me. I've sat in a lot of HAGS talks over the years, so I'm really excited to be on the other side of the podium up here talking to everybody tonight. We're going to go over a 3D model, a 3D data set that we prepared of attempting to model the surface topography beneath the Newark-Gettysburg Basin in southeastern Pennsylvania. I'm talking to you tonight, but this is a group project. I have co-authors for this data release. It's Morgan Baker, Craig Eversole, and our president here, Al. They all contributed to the processing, the geospatial analysis, data preparation, some model construction, some additional seismic profile interpretation. Ellen Fairs also assisted us with preparation and attribution of some of the digitized cross-sections that data you'll see. And Chris Oates also, he provided thoughtful insight into kind of the morphology of the Newark-Gettysburg Basin, and that kind of helped inform some of the decisions that I made in terms of the final model surface. This project was funded, it was completed with the matching funds from the USGS State Map program. A whole team of students from Harrisburg University of Science and Technology, their GIS group, they completed the initial georeferencing. There was a lot of work and the digitization of these geologic cross-sections that were used to build the 3D model. And then we also contracted with ARM Group to acquire and reprocess a seismic reflection profile, which was also used in the final model interpretation. As always, you can find our publications via PA Geo. It's available via this web address here or this QR code. When you click on publication search and draw in your area of interest, you can find publications relevant to the area that you're looking in. Our data releases, however, that's what we're talking about tonight. This is a data release product. They're not accessible via PA Geo. You have to go to either our DCNR webpage, the Geologic Publications and Data webpage, and you can go down to the Obtaining Geological Publications header, find this Pennsylvania Geological Survey publication zip file. And if you're not familiar with that, it's an Excel workbook, and it's organized by publication type and contains a description and data download links for all of the publications. You can also find data releases and then some select geologic data sets on PASDA's data portal. And for that, all you need to do is go down to search data by provider, select Pennsylvania DCNR, and you'll find all of our stuff. So please check those out if you haven't already, if you're not familiar. All right, so let's talk about modeling the base of the Mesozoic Basin. The survey has a goal of constructing a 3D framework model of Pennsylvania's geology, 3D into the subsurface. I think it was a few years ago, Al presented here at HAGS on the initial stages of a lot of the 3D surface modeling, and that included a depth to bedrock surface model. The Mesozoic Basin was targeted as one of the next subsurface features to map. And it's relatively, neatly contained in southeastern Pennsylvania. It features an unconformity that separates the Triassic sedimentary rock units from the underlying Paleozoic and Proterozoic rocks. And then the northern edge is characterized by these series of normal faults. And so it's just kind of a sensible choice for modeling. It's a complicated choice, but it's this distinct feature that would certainly be interesting to map. So this evening, I'm going to review the available data sources. We're going to talk about the GIS workflow that we ultimately employed to construct the model. And we'll also kind of have a discussion on how to adequately model the surface from this data set, which I think you'll see is actually quite limited despite extensive historical geologic mapping at the surface. But we'll also talk about what we can use the data set for and where we might go next. So again, the surface that we want to model in 3D space is the unconformity between the Triassic sedimentary formations and the adjacent Ordovician, Cambrian, and Proterozoic rocks. So it's this blue surface that I've kind of highlighted here in these profiles. We used a few different sources of subsurface data to put this together. The major data source for the project was a set of 66 interpretive geologic cross-sections. These were pulled from like 20-some reports that span from 1931 to 2025. They're Pennsylvania Geological Survey and US Geologic Survey publications. These black lines are the transects of the cross-sections, and as you can see, there's pretty decent coverage laterally across the basin. As I mentioned, we contracted with ARM Group to acquire, process, and reinterpret a seismic reflection profile line that transects Adams County and this gap here is Gettysburg, just to give you a point of reference. And really the most direct piece of information would be borehole data to get the elevations of the unconformity. There are several relatively deep boreholes in this part of the state, both from oil and gas exploration and some deeper water wells. But they're largely not deep enough. We'll get into the details of that in a minute, but the pink triangles you see here on the map, these are wells and boreholes that terminate in Triassic beds. The black cross hatches terminate in diabase. And then this lonely blue star is the only borehole with a readily available geologic log that I could find that intersects the unconformity. So ultimately, there were only 2 boreholes that ended up constraining the basin bottom, and there are these 2 here circled in blue. And of course, we have the mapped surface geology to give us the edges of the basin. So I want to take a closer look at the other data sources in a bit more detail and kind of give you a look at how they were incorporated. So Harrisburg University students, they really did a lot of work. They georeferenced those 20-some geologic maps. They digitized those cross-section transect lines. And then they took the scanned images of all of those geologic cross-sections. They lined them up to each transect, so they horizontally georeferenced them. And then the process that they used was to create line work, kind of in that flattened down. When you're looking at it in map view, it's like kind of off to the side, laying down. They digitized the line work there of the faults, the contacts, all of those features that are depicted in the cross section. And then they did a horizontal shift. And then they did a whole series of calculations they converted those lines to points and then used those calculations to kind of like, you want to think about them just kind of standing it up vertically where it needs to be along that transect line. So that's how they went through the process of horizontally georeferencing and then vertically georeferencing those scanned images of those cross sections. I'm not going to go into the details of their processes. It's a lot of steps and it's a lot of work, a little complicated. And I think that they already presented the details of their process last year at Central PA GIS Day. So the workflow is out there and it's really well documented if anyone's interested in the specifics of that. So what this kind of looks like in the 3D space, I have the outline of the basin here, and one cross section is shown, and we'll just kind of zoom in, and you can see how the cross section is kind of suspended or situated in 3D space, kind of hanging below the surface. And here's our faults and our contact lines. I'll turn it just a little bit more, and you can kind of compare it to their scanned cross-section image. And ultimately, we have 66 of those across the basin. So this is what that kind of looks like at the end. And I mean, I think this in and of itself is really interesting, and it's fun to look at. It's a neat data set of all of these fully digitized cross-sections. So for the seismic data, we have one profile that we're the seismic reflection profile line that ARM acquired and reprocessed. It was run in 1974, and the images that I saw of the original run were just not pull much out of it. And so they worked with, I think it was RDI, to reprocess that. And then they also did like an additional new interpretation. And this is the image of their reprocessing, which is a lot nicer to work with and pull information out of. On the left side of the screen, you have the northwestern side of Adams County. And on the right side of the screen, you have the southeastern border of Adams County. And we have the gap here in Gettysburg, but you can pretty quickly see you have this kind of U-shaped feature through the profile, and that's what's been picked out as the surface of the unconformity. So in the 3D space, this is what it looks like. In the front of this view, this is the border with Maryland. We're kind of looking into Adams County. Here's Gettysburg kind of floating at the surface. And here are the seismic profile pics for the unconformity that's underlying the basin. The total depth of that for the interpretation that we ended up using is at minus 17,000 feet in elevation. I think the one that one of their interpretations listed closer to minus 22,000 feet, so it's a little bit deeper, a little bit of variation there depending on how you want to choose to interpret that data. But you can see there's more of really a U shape here than what a lot of people might think of as the basin as like a strictly triangular wedge shape. So this is very interesting piece of data. And then for the borehole data, as I mentioned, a lot of them were too shallow to use. The majority of these wells that you see here, they were only they were terminated at 1,200 to 1,500 feet in depth, which places them roughly between minus 350 and minus 1,300 feet in elevation. So when we're talking about, looking into something to model something that's 17,000 feet deep, 20,000 feet deep, like they're not deep enough, not enough information, and most of them don't document the unconformity. I'm going to show you some video clips. And hopefully it's a bit easier for the bandwidth of people online. But the two wells that I did end up using to constrain the framework of the model were two Donaldson exploration wells that were drilled in the 60s in, I think, Newark County. This orange one that you see here at minus 795 feet. That's the live well, and it did document the unconformity here at 7,300 feet below ground surface. So that's our sole empirical data point. The other well that was useful is another Donaldson well, the fixed well. While it did not get to a depth at the unconformity, it was used to tighten up the constructed contours of the framework, basically just to keep its location at almost minus 1,300 feet, to keep that location vertically above the modeled unconformity elevation. And you can kind of see how these contours were kind of tightened up. They were kind of tugged up to accommodate that piece. There is another very deep well in the basin, on the other side of the basin, along the edge of the Newark portion. This is the Cabot KBI well, which was drilled in 1975. And it goes down to 10,500 feet below the ground surface, which with a slightly minus 10,018 feet then elevation. But it did not reach the unconformity. And I've just kind of shown it to you here how it, although it's very deep, it wasn't really used to constrain any parts of the model framework. So it wasn't really included as an input point. The aqua line that you see at the bottom of the basin here, this represents minus 12,000 feet in elevation. So really the bulk of the data used in this project is coming from the cross sections. When we strip away any information that's not the unconformity out of those cross sections, this is what we're left with. We have the well bores here in purple and orange. We have the seismic profile, and then everything else is coming from the cross sections. And you'll notice that they're hugged tightly to the edge of the basin. Those cross sections are not interpreted to a great depth. There are two that extend. You see that the unconformity extends the entire way across the basin. Those are two USGS cross sections that did complete their interpretations to a depth below the unconformity, and so we have those pieces to use as a guide across the basin. But when we're thinking about essentially interpolating data points to create a surface, and we're limited to this shallow data, we really don't have any empirical data at depth of, towards the bottom of the basin. So our initial plan essentially was to directly interpolate this information kind of as separate fault blocks and stitch it together at the end. And that was the mental plan that we were working with. And then we got to this point, we realized, well, that's not really going to work with the information that we have. And so we'll have to take a different approach. Some of you might be wondering why we're using a GIS software to model a complex regional geologic basin. At the time of the proposal, and really not until last summer or fall, ArcGIS was the only 3D capable software that we had access to. I think our procurement process has come around, and we've acquired some of these more sophisticated softwares, and we're planning on using them on other projects. And we're all very excited about it. But when this model was constructed last spring, ArcGIS was the tool we had. And that's okay. It's still a widely used tool, and it worked for our process. We have a 94-year spread among the geologic interpretations. And we have a variety of resolutions. Right? Mapping was done by different people with scales. We have a variety of confidence in some of the input data. The seismic profile reprocessing was definitely successful, although that seismic profile is an old piece of data itself. And we only have a couple of hard data points at high resolution. Right? This is not textbook. So there are definitely some limitations. to the final product. But let's step back to the conception of this project. What we're trying to accomplish is a 3D subsurface interpretation of geologic features in the entire state. We have a wealth of digital and non-digital information available to us, and we're steadily digitizing, scanning, inventorying, building data sets, preserving and managing so much data here. There's always a discussion going on about how to incorporate it, how to make it more accessible for our purposes, how to make it more accessible to the public. And so this project really provides a great opportunity for a case study on how to piece it all together. Let's take these legacy geologic interpretations across a region and really see how we can incorporate them with modern data sets to derive a new interpretation. Right, we're putting together a new digital product here. And by doing so, we're going to be able to clearly see where the gaps are in the information that we do have. We're going to see very clearly what's available, and it allows us to plan for future mapping and plan for future improvements. So I'm going to kind of ask you to look at the final product and join me in a little suspension of disbelief. And keep in mind that I'm not presenting the model of the base of the Mesozoic basin. I'm presenting a model. It's our starting point to be refined through iterations that we do with any model. So in order to put this together, we ended up just using more of a manual process of constructing a scaffolding framework. If you want to think of them as ribs, the kind of the transverse portions of that framework stretching across the basin, those are pieced together from the seismic profile, the borehole data, and the cross sections. The pieces here that you see in gold are what was extracted as an unconformity. This purple line here is the seismic profile. And when we take those cross sections and extrapolate the contact angle of the unconformity to a depth, that's how we're extending the framework of the model deeper into the bottom of the basin. And those are those green lines that you see on the screen. So essentially what we've done is take the cross sections, they're drawing the unconformity, they stop at some point, and we just extend that line literally into the subsurface. Why a linear extrapolation? Well, it's just the simplest place to start. Any areas without interpretations, so these gaps between cross sections, kind of dummy extrapolations were constructed to use as a guide. And so we take these lines and construct the contours. They were constructed at 1,000-foot intervals and essentially manually connecting the dots between these lines as they go down into the subsurface, adjusting as needed if conflicts arose or if it seemed more reasonable to kind of mirror the shape that one cross-section provided versus another, or mirror the general shape based on fault locations. This is what the contours look like in plan view. So we're going from red to purple, shallow to deep. These minus 20,000 foot sections here, these two, these are the deepest parts of the basin, and I terminated those at 20,000 feet and just kind of flattened it out there. What's happening is that the cross sections in these areas are interpreting the surface of the unconformity as essentially almost taking like a nosedive into the subsurface. And so they are going down in these really steep angles, and there's no convergence happening with the extrapolated lines from the cross sections over here to the ones here. They do meet, but it's much, much deeper, and it's just really an unreasonable depth. So I just made the decision to terminate 20,000 feet. These are areas where we really need more subsurface data. We need more information about the faults at depth, and the angles of the unconformity of that surface. The 16,000 foot area here on the western side, that's mostly informed by the seismic profile, the more shallower interpretation. Here around Lebanon County in this neck area, it's very shallow at minus 3,000 feet in elevation. And that's really highlighting that we're mostly looking at the sedimentary rocks. We're not really accounting for the full thickness of the diabase intrusions, especially in that area. So when we can get better information on those and really the morphology of those and how thick they are across the board, I would imagine that this number would get deeper or get larger. And then in the newer portion of the basin, we have better convergence of the extrapolations. It's a bit shallower at minus 12,000, minus 13,000 feet of elevation. And as I mentioned, we have those two cross sections that span the entirety of the basin, and those are really informing a lot of the shape that you see in that area. We need to turn this framework into a surface. The way that we chose to do that is to convert these contour lines and convert the superficial geologic boundary here into points. We'll add in the seismic profile text, we'll add in a borehole, and what we end up with is more than 8,000 input points that are used to generate interpolations of the basin bottom. So how do we communicate variable resolution source data in a derivative map product? When you're interpolating a surface, the resulting raster is a series of uniformly sized grid cells, each containing data. There is an implicit data precision that goes along with the raster resolution. You expect a high amount of precision with a finely gridded surface, and as that grid coarsens, you expect lower precision to go along with that. Here, most of the information below 2,000 feet is really a guess. If I make a nice looking surface with tightly spaced grid, well, is that really representing the cross sections and the information and the confidence that we have behind those, especially as they're extended deeper beyond what they were interpreted as? No, it doesn't. At the same time, I do have a lot of confidence in the immediate area around that borehole, right? So I don't know, how do we manage all of this variety? If we divorce ourselves from the idea of a raster as the only way to visualize a surface, and instead of look at a data set of points, well, then we can space those points however we want. They're not restricted. So what we ended up doing was generating 4 natural neighbor interpolations to represent varying levels of data density, resolution, and interpretive confidence across the basin. So we have 4 different rasters, 4 different interpolations, increasing the larger grid cell sizes. So the first one has a 40-foot grid cell, just up to 400 feet, 800 feet, 1,600-foot grid cells. We've kind of named these tiers. So tier 1, the really fine grid, is meant to be used in areas of the empirical data. Tier 2 and tier 3 are for different levels of confidence for our interpretive data, so our seismic profile and cross sections. And then tier 4, the coarsest grid, is meant to be used for areas of extrapolation, really the deepest parts of the basin. So in order to put those all together, what I ended up doing was taking the source data and buffering it to clip those rasters. So tier 1 is our borehole. we have a 400-foot buffer. In green, you can see tier 2 data with its 4,000-foot buffer. Tier 3 is the space between those interpretations. It's that sugar orange color, it's 8,000 feet buffer. And then tier 4 is anything remainder, it's all that extrapolated information. So basically, I'm taking the buffer for tier 1, I'm going back to my raster and I'm clipping the number 1 raster. And I'm taking my tier 2 data and I'm going back to my number 2 raster and flipping that. And then doing the same thing with tier 3. And then the remainder is tier 4. And then points were extracted from each of those clippings and then merged together into one point-based 3D surface. It's one data set then. And we have our surface representing varying grid size patterns. So these snapshots here, zoomed in a bit, kind of showing what the data looks like. These are color-coded by tiers again. Here's our borehole data points. As we step over to tier 2 in green, you can see the grid getting a bit wider, and then tier 3 with our medium interpretation level, the grid gets a bit wider, and the pink dots in the extrapolated zone for tier 4 have the widest grid. What we end up with is about 97,000 points representing the model basin bottom, multiple spatial resolutions. I just kind of put this little video together here to give you a zoom around to get a feel of it. Again, the points are colored by those tier classifications. But we were able to kind of digitally weave these legacy geologic interpretations with more modern data and more modern interpretations and use them to produce a new product. We managed to put this together in ArcScene in a GIS environment. And this data set and workflow can be used as a guide for future 3D subsurface mapping. And now we really have a better handle on what to expect out of these older geologic cross sections and what we can get out of them, and some ideas of what we can use them for. So here we're looking, handing over to the newer portion of the basin. On the right-hand side will be the Delaware River. We're going to kind of turn around, take a look back at the Lebanon area, and then we'll kind of zoom back, close out again, looking at Adams County. I think that one of the major areas of improvement is related to all of these kind of drop-off cliffs that we kind of have from these geologic interpretations. We use this model, it can be used to plan for future refinement, future areas of mapping, future areas of data collection. Many of the tasks that would make this a more accurate model were really just outside of the scope of the project and outside of the scope of the grant proposal. If we have a dedicated allotment of time injecting faults into the subsurface, that can provide constraints into the shape of some of these walls. In areas where we have wide distances between cross sections, those could be revisited. New interpretations maybe could be added to this, and either as a standalone investigation or as part of future mapping efforts paired with those. What we really need is dedicated efforts to collect subsurface geophysical surveys, subsurface really deep borehole data, basin-wide. We need that information. Sorely needed. As I mentioned, I think the biggest area of improvement would be to address the nearly vertical walls that prop up around in the basin. what I want to show you in this video is the difference between the cross sections from the 1930s in Adams County and the seismic profile checks. So what you're going to watch is kind of a lot to take in. It's a little tricky. So I'm going to orient you before I hit play. The rainbow contours from the edge of the basin, the unconformity surface, the red and the mostly white horizontal points, these are parts of the cross sections. The red dots, those are the unconformity. The white dots are kind of showing you the limit of those cross sections. The rainbow points going kind of diagonally in space, those are pulled from the extrapolated lines of the unconformity surface. Our seismic profile text are here, these red diamonds. And so you can see kind of as we look around, you can get a feel for how these cross sections were some of the ones that show this nosedive with the unconformity surface. And so when we extrapolate that same angle to depth, you end up with this really sharp wall. And coming from the other side, you can see this really nice triangular wedge shape that we get. But as we spin around here now and look from the underside of the basin, you can see how those lines might converge and those wedge shapes and how much they really differ. We're at the northern side of the basin here looking into it. This is the tricky part. Give it a minute to turn around. You can really see the difference in the shape of that wedge versus that lovely, almost broad U shape from the seismic profile. And how those are two very different interpretations. If you go with the wedges, you know, the deepest part of the basin is at a totally different location than what's shown in the seismic profile. So you look at the other side of the basin in Newark, there is another seismic profile. This is from with Jack and others from their 2013 publication. In their diagram here, this Cabot well is, I'm pretty sure it's the same one I showed you earlier. It was drilled to 10,500 people in service. This profile shows two relatively, compared to a steep drop off, relatively gentle slopes of these wedges, these really nice triangular wedge shapes between the faults. I didn't end up using this, we didn't use this, there's no depths associated with this profile, at least not publicly, but this is something to pursue the next step, because as you'll see in the next slide, it's really a great example of two things. One, that there are likely other spots in the basin that should be adjusted to a different topographic profile, like in the Adams County area. And two, we really don't have a good handle on where or how drastically any of the slope changes occur along the basin walls. So like this profile is really nice, triangular shape. The sides the slopes are very consistent all the way to depth. But like in the Adams County seismic profile, that's more of a U-shape, totally different shape. And the slopes change angles as you go deeper. They are not consistent. It's not the same angle all the way down. So on one side of the basin, you have one shape, and on the other side of the basin, you have a totally different shape. And what's happening in between? When does it transition? How does it transition? We just don't have that information. So this is looking top down on the Newark side of the basin. This is generally where that seismic profile was run. And here's that Cabot well again. You'll see that I have these kind of gently stepping down contours on the southern side of those wedges like the seismic profile had. And that matches what's shown in the cross-section from the USGS, that larger one. But I use the information from the USGS cross-section to inform this steep drop-off on the northern side of this wedge, which does not correspond to what's shown in that seismic profile. Similarly, on the northernmost side of the basin, you have another one of those steep drop-offs, and that's informed from this series of cross-sections here in the northeastern corner. And you'll notice that they don't agree with the USGS contour cross-section. The USGS cross-section is showing a much more gentle slope, which is what was shown in the profile. So really, my point here is that we need to spend more time collecting more subsurface data to confirm or tighten up the morphology of some of these areas. And I think that would go a long way to improve the model overall, and would definitely provide for some interesting research for some. So I want to leave you with something fun tonight. We're not only stepping our way into the digital 3D space here at the survey, but also the physical. Adam Hayano here at the survey, he's been experimenting with 3D printing, and he's prepared these really neat 3D printouts of the topography of Pennsylvania. They're these nice little handheld items. These are really meant for outreach purposes. But he also printed out a model of the Mesozoic Basin. So if you're here tonight, they're really fun to look at. Please check them out. Just be gentle, I guess. So
the narrow necks are called that for a reason.
Yes, that's a snap point for sure. So anyway, that's what I have to share with you tonight, and I'm happy to take any questions. Thanks so much for your attention, and also welcome a discussion or an email about the final shape of things and how to, refine it. Thanks.
I want to provide some context. So we're going to put together a 3D framework model of the whole state. Well, we're not the only state. All the other geologic surveys are also in varying progress along this journey. What's important about? Oh yeah. I am. All right. So what's important about this approach is I've been a strong advocate when I'm talking to the other state surveys and how do you present three-dimensional data? And traditionally, and this is nothing new, right? We've been doing 3D data for a long time. Structure contour maps. Any geologic map that has structure contours, that's representing 3D surfaces. My issue with structure contours is a contour line cannot in itself convey confidence. So that's why going about this process of having point data, because each point can then be attributed to what tier it is, how confident we are in this elevation. So that's something that we're having conversations at a nationwide forum and talking about what's the best way to realistically portray three-dimensional data. And I'm a big proponent of point data because we can then also communicate out our level of confidence. And this is a good example. This project was a good example of that. We created structure contour maps and we published that out, and that's gospel. That's it. Like, no, now we put up these points and we're putting all these caveats on it. Like, well, some points are better than others. So just to give you that as context, do you guys have any questions for Liz? Because I have some online.
Get the Cabot KBI well, was out of Bucks County, correct?
Yeah.
There was a second well drilled, I think, Montgomery. Was that outside? That was outside of the basin. It was.
I don't know. There are a few other boreholes that I found locations for from our records. But when I was digging through Edwin, and I didn't go through the process of trying to dig out the paper records on the other side of the state, and I don't want to bother those guys and spend all this time, but I couldn't find the logs for them.
Okay.
So I found the locations, and then there's also several boreholes that you can get from USGS's borehole data set, but none of them are interpreted because they have the wireline logs, but that was just really out of the scope of delving into those. So there's a couple other options available to look at.
Okay, what's this other software you're going to use?
It's long, it's a few.
We have a couple now. Aquavea's GMS, which I have experience with that previous life. We have Rockworks, which also does some 3D. So yeah, we're exploring some.
Are you counting like steps software?
You know, we don't have that in house yet.
Okay.
It takes us a long time to secure software.
We were ARC, I was ARC forever. So,
Yes.
okay.
And Bill,
Yeah, there's another seismic line through the thin neck there where you've got 3,000 foot. It's the 2008 data we collected through their southern Lebanon, northern Langston. It shows
Really
the
nicely.
base, but it's that whole data set was processed for the deep data, so it's usable, but it needs to be reprocessed for the Triassic part of it, but it's imaged there. And you can see it's shallow, and it's, Al and I were talking about it. There's high reflectivity. And you go, is that the underlying Paleozoic? Is it the basalt? Is it, so there's some uncertainty, but it is shallow as you represent. Definitely appears to be shallow.
That's good. I understand too that the width check group is working on that area right now too. They're kind of detailed mapping. They're doing their interpretations.
Ben Greeley asked, are you familiar with the fail basin interpretation? Didn't I see you have a follow-up slide on that?
In a sense, I'm just gonna say I'm not a structural geologist. I'm a hydrogeologist, but yeah, well, I did pull this from his paper. I really like this diagram that he has in there. Is there a follow-up question or just?
No, that's it.
Yeah.
I wanted to put it, Ben, yes, we are familiar. You even had a back.
I like this diagram and how he was thinking about the basin in terms of chunking out these different similar blocks. And, maybe when we were initially kind of thinking about chunking it out ourselves, maybe this was something that we were going to kind of use as a guide, but didn't really.
Yeah, we just didn't have near enough density of data to do that resolution. Some more comments online. The best science provokes more questions than it provides answers. This is a good example of that. Great job. Would it be possible to link the data with the New Jersey basin boreholes for most? Yeah, I mean, that's. Sorry.
Yes. Yeah. And Maryland,
See, that's the fun thing. All these states, we're all going to be creating these 3D, and eventually we got to stitch them all together.
that's the USGS's problem.
That's right. Did you guys have any? I'll keep reading unless you guys have a question. Aaron likes the idea of increasing the pixel size. Tony says it's a great study for future 3D mapping. And now Ben's back with, there was a well that punched through the Bucks County diabase sheet into the Stockton below. But it still didn't penetrate the
That's
basin.
interesting.
Yeah. Yeah, Bill.
I thought it was interesting, the seismic line that you showed on the eastern side, that published one. There's very little indication that I can see of diabase in there, yet the Gettysburg line itself has all kinds of diabase. So I think that in itself is worth investigating, the relationship of these secondary faults and the surface exposure of diabase.
Well, conveniently or not, it's between the diabase. Is where
Yeah, right. They put it right between, so that's really, I thought that was really interesting, and that's where they drilled. And I'm surprised they sold that well, being so close to something that hot, obviously. But I would think a lot of what's driving this is, metal industry. You got Cornwall on the north side, then you got Grace Mine. That's, billions of dollars worth of iron ore that you can now evidently image. You guys are studying it. This is coming to light, and we can actually study this if you can explore for this. I would think you're getting calls from that side of the world.
Yes, the diabase is it is a hot topic. So we get a lot. We have diabase core in our library. We have quest for it. Yeah, because of its mineral potential, especially in the big zone. So yeah, there's a lot of interest. So Liz mentioned at the beginning how we chose this basin because of its limited geographic extent. Yeah, that was it. And probably much more complicated than we were anticipating. So our next project from the 3D framework is we're going to look at, we're choosing major surfaces. So we did the top of the bedrock. We got basement. We have the basement surface for most of the state. We're still working on that. But our next project is going to be the Mississippian Pennsylvania unconformity out in western Pennsylvania. To try to, what can we model in subsurface that is a through-going surface? So the idea here is that we build this framework, we're taking all of these major unconformities, major surfaces. Once we have that all framed out, then we can start infilling with more detail. So stay tuned, more to come on that. I foolishly promised Gail that I would have this framework model of the whole state done by 2030. Which at the time seemed like a long time ago. Now it doesn't seem that. It was like just around the corner. Any final questions for Liz before we adjourn for the evening? Thank you, Liz. Great job.